Salam sejahtera, Dr. Saya Hakim. In this experiment, blocking of struts, I will begin my part. This is the introduction of this experiment. So, from the side, we can see clearly the blocking of struts. That one is the up of the. We have the two end restraints conditions. This one is the on above, and this one is as below. So we can set up, follow, and based on our lab conditions, this one is the pin connect to the pin restraints, and pin connect to the fixed, and the fixed connect to the fixed conditions. So the objective is to examine how stress response varies with an increasing point of load, to examine how shear force varies at the cut positions of the beam for various loading conditions. The theory in this experiment is to predict the blocking load. Euler blocking formula is used by the formula moment of the initials I equal to BD power 3 divided by 12. The formula for the Euler blocking is the PE equal to the pi power 2 times the E times I divided by 0.7 length power 2. So a comparison between the experimental and the theory blocking load are recorded. So after we done the experiment, we will do the comparison between the experimental and theoretical value of the result. So for the setup, the apparatus, there are the three types of the restraints. This one is the pin to pin, the restraint, and the pin to fix connector, and the fix to fix restraints. This one is the mean that the one of the connector is the fixed support, and one of the connector is the pin support. So we in this experiment we use the 5 type of the struts. That one have the 0.32 meter, 0.37 meter, 0.42 meters, 0.47 meter, and last 0.52 meter.
Okay, so now we move to procedure. For part 1, the machine was filled with the button chuck and the top chuck was removed. The shortest strut, number 1, was selected and the cross-section was measured using the provided vernier. The second moment of error, 1, was calculated for the strut, BD of 3/12. Number 2, the position of the sliding cross head is adjusted to accommodate the strut using the thumb nut to lock off the slider. It is ensured that the maximum amount of travel is available on the handwheel thread to compress the strut. Finally, the lock screw is tight. Number 3, the handwheel is carefully back off so that the strut rests in the notch without transmitting any load. The force meter is rezeroed using the front panel control. Number 4, the strut is carefully loaded. If the strut begins to buckle to the left, it is flicked to the right and vice versa. The hand wheel is turned until there is no further increase in the load. So lastly, the final load is recorded in the table 1. The process is repeated with strut number 2, 3, 4, and 5, adjusting the crosshead and as needed to fit the strut. So part 2, number 1, the effect of end condition is studied by following the same basic procedure as in part 1, but this time the bottom chuck is removed, and the specimen is clamped using the cap head screw and plate to create a pin fix end condition. The results are recorded in table 2, and the values of 1/L/2 for the struts are calculated. Number 3, the top chuck is fit with the 2 cap head screw, and both end of the specimen are clamped to create a pin end condition. To new values of L1/L/2 are calculated. The result was entered. Lastly, the result was entered into table 3.
For this experiment, we use struts with different length. for the table 1 result for pin ends, we use the formula P equals to pi to the power of 2 times with Young modulus time with second moment of area and divide with the length of struts to the power of 2. And with that we got 88.65 Newton. For this table 2, result for pin fixed end, we use the formula P equals to pi to the power of 2 times with Young modulus times with second moment of area and divide with 0.7 length of struts to the power of 2. And with that, we got 126.64 Newton. For this table 3, results for the fixed end, we use the formula P equals to pi to the power of 2 times with Young modulus times with second moment of area and divide with 0.5 lengths of struts to the power of 2, and with that we got 177.3 Newton.
The L-belt buckling equation is formula that describes the buckling load of the slender column subjected to compressive load. It is based on the equation P equal to 2 EI over L power of 2, where P is regular buckling load, E is the Young modulus, I is the second moment of area, and L is the length of the strut. The equations show a linear relationship between the buckling load and length, with the load decreasing as a strut length increase. An experiment confirmed this linear relationship, and the L buckling equation are reliable tool for the design for the slender struts subjected to axial load. The study revealed that end conditions significantly influence the strut buckling load. Experimental ratio for the pin fixed and fixed end condition divide from the theoretical of 1 suggestion potential error. However, theoretical ratio show that the fixed end condition offer high buckling resistance that pin end condition. Fix and prevent rotation, increase stiffness and stability, and require more force to induce buckling. The observed doubling of experimental ratio when one end change from pin to fix support this conclusion.
For the conclusion buckling of struts, the result of the experiment showed a linearity between the load and length. The longer strut experience a lower buckling load process when compared to shorter strut. Both have the same material properties, and the difference is seen through the length of the strut, which cause different deflection to result. The linear elastic behavior is shown through the photograph. The assessment is that by reducing the length and increasing the cross-section of the strut, the critical buckling load is higher, making the material resistant to buckling at higher applied loads. A linear relationship is shown on the graph. That's all our conclusion, and thank you.